Hello, I'm Sam Howard, and this presentation is on characterization of HIFU fields inside of a tissue-mimicking HIFU phantom. First, some background and motivation. Phantoms are obviously useful for HIFU, for dosimetry, as well as checking on the performance of HIFU equipment. Prior to 2003, thermal phantoms were introduced based on polyacrylamide as the phantom matrix, with albumin added as a marker inside of that matrix. The albumin, upon achieving a temperature, would denature and change optically, or its performance in magnetic resonance imaging equipment would change. The issue here is that in order to achieve realistic acoustic attenuation, typically large scatterers were added in order to achieve that attenuation. And these scatterers were large compared with the optical wavelength. So visual detection could sometimes be obscured by those large optical scatterers. In 2003, my company introduced a proprietary polyacrylamide formulation, which had some proprietary additional components that allowed realistic attenuation without adding those scatterers, so that the lesion formation was very clearly delineated. Presently, we're investigating the use of this phantom with optical hydrophone so that pressure can be measured inside of the phantom. Here's an example of the original optical use of the phantom. It turns opaque at approximately 70 degrees Celsius. This makes it useful for checking the consistency of transducer performance, as well as also for thermal modeling of HIFU dosage. These are some acoustic properties showing that the attenuation and velocity are very similar to many tissues. Density being very close to water also makes the impedance very similar. Here's some thermal modeling examples of the growth of a lesion over time with leaving on a 10-watt f1 4 megahertz HIFU source with modeling done in finite elements for what the growth of a lesion should be. The present work discusses the use of another product of ours, a fiber optic hydrophone, where it is embedded in the HIFU phantom. The fiber optic hydrophone is very well suited for measuring HIFU because of its wide bandwidth and ability to withstand high pressures up to hundreds of megapascals. The use with this particular phantom is very attractive because of the optical clarity of the phantom and the lack of large scatterers which would interfere with the operation of the hydrophone. This is an example of the calibration which was done in water for the phantom. Here is the setup. The phantom is encased in this plastic box. The fiber is introduced through a cannula at the bottom of the box, and it's being sonicated by the transducer at the top of the box with a transducer which is 3.74 megahertz f1 transducer. And here are some results. In blue, you see the measurement of the waveform in terms of pressure, both in water and in gel using the same transducer. This was all assuming that the same calibration that was done in water was good for gel. In addition, we modeled the pressure field assuming a 15 millimeter equivalent source diameter and the same nonlinearity parameter B over A for the gel as for water, with results that are fairly good. These were results at the maximum pressure achieved before we started to see cavitation in the gel, which occurred at around 7 megapascals peak negative pressure. In terms of the next steps, Obviously, we would like to rigorously define the calibration in gel, probably with respect to a source transducer. Also improve the source model and also obtain the nonlinear parameters for the gel for higher accuracy. And this will allow us to rigorously evaluate the HFO measurement to understand what the uncertainties in this measurement are. Also, we'd like to explore improvements in the pressure limits for the gel, particularly by degassing. And finally, refine the apparatus, basically making it larger to allow some scanning of the source relative to the hydrophone so we can get some more beam profile information. I thank you.